Module 5 generalizes the concepts of simple linear regression to allow for the possibility of more than one independent variable. In the general multiple linear regression model, we'll denote the number of independent variables with the letter k. When k equals 1, the concepts are those of simple linear regression. In multiple linear regression, k can be 1 or 2 or 3 or theoretically any number of independent variables. Here's the general multiple linear regression model. It says at a population or process or theoretical level that the value of the dependent variable y can be described as a linear function of the independent variables x1, x2 through xk. The intercept term is beta naught. The coefficient of the x1 variable is beta 1. The coefficient of the x2 variable is beta 2, etc. Sometimes beta 1 is referred to as the slope or partial slope for x1, and beta 2 is referred to as the slope or partial slope for x2, and so forth. In section 14.2, multiple linear regression measures of variation are introduced. These are predominantly the same measures of variation as those of simple linear regression. For example, we'll see SSR, SSE, SST. We'll see the coefficient of determination, R squared, and so forth. There's a hypothesis test for the overall usefulness of the model. The null hypothesis says all of the slopes are equal to 0. That is, whatever x value is plugged in will be multiplied by 0, and the multiple linear regression model is not useful. The alternative hypothesis says at least one of the slopes is different from 0. That is, at least for one of the variables, when an x is plugged in, the estimate of y will change. That is, the multiple linear regression model is useful. This hypothesis test for overall model utility uses MSR over MSE as an F test statistic. Section 14.3 describes the multiple linear regression model assumptions, which are essentially the same line assumptions as those in simple linear regression. The required residual analysis to check the model assumptions is a straightforward generalization of the simple linear regression residual analysis, but requiring a few more residual plots. Section 14.4 involves two more results. The first is a hypothesis test for the usefulness of the specific independent variable xj. For instance, we may be asking, is the x1 variable useful in the model? H0 says the slope for xj is 0. That is, when any xj value is entered, it will be multiplied by 0 and won't change the estimation of the y value. That is, xj is not a useful variable in this multiple linear regression model. The alternative hypothesis, on the other hand, says the coefficient of the xj variable is different from 0, and thus xj is a useful variable in the multiple linear regression model. This result uses Bj over Sbj as a t-test statistic. The second result is for a 101 minus alpha % confidence interval for beta j, a particular slope. This result is essentially the same as that for the slope of the simple linear regression equation. We're going to omit section 14.5, testing portions of the multiple regression model. In section 14.6, the new material involves creating and using an interaction independent variable. We do this by multiplying two existing independent variables. Throughout Chapter 14, we'll illustrate multiple linear regression concepts using an example in which radio advertising expenditures and newspaper advertising expenditures are used as independent variables in an attempt to predict a dependent variable y, sales. In section 14.6, we'll ask if the interaction between the audio advertising variable, radio, and the visual advertising variable, newspaper, can be used to better predict sales. This is a question of the importance of the advertising mix. In homework 5, you'll be asked to determine whether the interaction of an aisle location variable, front aisle or other than front aisle, and a shelf space allocation variable in feet can be used to better predict sales. This completes this screencast.